Well, thanks for having me. It's just a gorgeous place, I have to say. I really enjoy my stay. Um, I should also say that Vladi was supposed to give a talk. Unfortunately, fell ill the evening before. He seems better in North Carolina, and we wish him all the best. You can actually see his talk, the one he would have given. It is posted on the website, so I invite you to take a look at that. This is also work with Chandradoy Chattopadhyay, who was here earlier, gave a talk about a different subject. I also encourage you to look at that, a beautiful talk. And finally, this includes Josh Ott, who's an undergraduate at North Carolina. He just graduated, and he will be a grad student at MIT in the fall. So the motivation for this work is the attempt to locate the actual phase transition between a quark-gluon plasma and a hadronic gas. So obviously there's somehow evidence, and we can argue forever how good the evidence is that we've seen a quark-gluon plasma, but because the phase transition at the highest energies is along the temperature axis where it's known to be just a crossover, there is no immediate evidence of an actual sharp phase transition in any of the data. And so there are two possible things that could imply that there is critical dynamics. One is the fact that if you tune the quark masses to zero, there is an actual second order phase transition related to chiral symmetry. So that means there's an axis in this diagram where you take the quark mass to zero, and in that sense, you have a nearby phase transition, and that nearby phase transition can, of course, affect the dynamics. The other idea is that eventually, as you go to high baryon density, this crossover might turn into a first order transition, which would then end at a critical endpoint. And so that also could be a nearby critical point that's potentially visible in actual data from heavy ion collisions. And so here, of course, you would somehow look at chiral fluctuations, and in the vicinity of a critical point, you would look at fluctuations of the baryon density. Now, the workhorse for describing the dynamics, and the reason we're here, is that the data are well described by fluid dynamics. So if one wants to describe the dynamics near a critical point, the question is, what is the relevant theory? And of course, the basic logic of fluid dynamics still applies, that that's the relevant long distance theory, but there are a number of things that we now have to include. So for one, we obviously need an equation of state that actually includes critical features, that has, as you take the quark masses to zero, or as you tune the baryon chemical potential, has an actual critical point in it. Since we're interested in fluctuations, and since fluctuations become large in the vicinity of critical point, we of course have to now include these stochastic fluxes. And once you do that, the important symmetry that you have to respect are fluctuation dissipation relations. So usually when we do fluid dynamics, there's only dissipation, but there's no fluctuations, right? And now that becomes crucial. And finally, there may be additional there may be Goldstone modes, such as the chiral field in QCD. Now, hydrodynamic theories of this type were originally classified by Hornberg and Halperin in a famous review from 1977, and they have these funny names that are not very inventive. They're just called Model A, Model B, Model C, and so on. And the two theories that we think are potentially relevant to QCD is the critical dynamics of a chiral phase transition. So that's some kind of O4 magnet. In fact, in the language of these models, it's an O4 antiferromagnet, and antiferromagnets were called Model G by Hornberg and Halperin, and that was pointed out already in the early 90s by Rajagopal and Wilczek that Model G is the relevant hydrodynamic theory for the chiral phase transition in QCD. But then somehow, I don't know, the world took a detour and people had all sorts of crazy ideas as to what might be seen, that nobody really ever studied this model until quite recently. And now, of course, last week, Derek gave a talk about Model G. And then in addition to that, there's this possible critical endpoint. And as was pointed out by Son and Stefanov in the early 2000s, that critical endpoint we would expect to be in the universality class of Model H, which is the same theory that describes the liquid gas endpoint in ordinary water. Okay, so that's the theory I wish to look at. Now, these theories, to have a really simple side, these theories are really constructed in analogy to kind of ordinary Brownian motion. Brownian motion is in some sense the simplest example you can keep in the back of your mind. So if you think of a Brownian particle, it could evolve to ordinary classical forces, which I haven't even written down here. So there's a sort of ideal dynamics, but then there's drag on the particle with some kind of drag coefficient that I call gamma d. And then the crucial point about Brownian motion is, of course, these stochastic kicks. Okay? And if we look at sufficiently long distances, we imagine that these things are totally uncorrelated, so that at least approximately this just looks at like white noise. So successive kicks are completely uncorrelated, and it's just characterized by some overall strength. So this is Gaussian noise. That's what you can do better eventually, but this is the simplest model. Now, we expect that the particle will eventually thermalize if it moves around for long enough, meaning that the mean square momentum at that point is entirely governed by just the temperature of the fluid, and it should be independent of this gamma and independent of this kappa. But that, of course, requires some kind of conspiracy, right? That on average, the energy you take out by drag is always being put back in by noise. And so that requires a relation between drag and noise, and that's one of these fluctuation dissipation relations, that the product of drag and noise is just given by temperature. Okay. So here's then this model H, which is written in exactly the same way. So this contains two fields. One is some kind of order parameter field, which you can think of as the entropy per particle, or something like the density minus the critical density. And that order parameter is subject to diffusion, characterized by some kind of conductivity, and it's coupled to the momentum density of the fluid. So it's being carried around by the momentum density of the fluid. So there's some kind of advection term, and then it's subject to noise. And the momentum density basically evolves by the Navier-Stokes equation to transverse components of the momentum density, and I'll say something about that in just a second. So these are ordinarily purely diffusive, so they evolve diffusively governed by the shear viscosity, but now they're also being advected by this order parameter. So this is an advection term, and then of course they self-advect. So this is the ordinary nonlinearity in the Euler equation, and they're subject to noise. And here, all of this is written in terms of some kind of free energy functional. In principle, that can be a very complicated function of the fields, but near a critical point, again, we can use a Landau-Ginzburg type functional that just governs or represents the critical dynamics. And so in this case, what we need is a critical functional for this order parameter field that has the capability of describing a second order endpoint, and the simplest one of this kind is just an Ising functional. And the only thing that's really new, if you wish, compared to ordinary fluid dynamics is that now there's gradient terms in the free energy. And the reason we need that is that because in the vicinity of this critical point, so at the mean field level, m squared would go to 0, so there's no kind of restoring force, the speed of sound goes to 0, and then this term becomes irrelevant. Okay? And here it's simply quadratic in the momentum density. Again, that's the approximation we usually make. Mhm. So I will say something about relativity only in the very end. We actually think that the critical dynamics of the relativistic theory is exactly the same, in the local, if it's not moving, if it's not expanding rapidly, if it's just sitting in a box, then the critical theory would be exactly the same, because these are extremely infrared modes that I'm studying. So the relativity question will be the one that, of course, eventually we care about, which is what happens if this thing gets advected by some very rapidly expanding fluid? What is the best way to do that? So for now, this theory will indeed just look completely non-relativistic. Right? Yes, phi is the order parameter. Well, okay, these are extremely slowly evolving modes, right? They don't care about the light cone is way off in the distance, and some mode that's evolving super slowly, right? So that's why, roughly speaking, relativity doesn't matter. Now, again, it does matter if you actually want to embed this into a real relativistic fluid, and we have to figure out what's the best way to do this. Okay. But today, I will not say much about it, except to say that, I think the right way to do this is the discussion that Derek gave in the afternoon last week, which is that this very naturally embeds into this kind of density frame, which is, of course, what we're trying right now. Okay. So again, we had these two fields. They're subject to noise. And again, the strength of the noise, it's white noise. It's governed by these fluctuation dissipation relations, meaning the strength of the noise is given by the transport coefficient, the conductivity, the viscosity. And that's supposed to ensure exactly the same thing that was supposed to ensure in the case of the Brownian motion, which is that the equilibrium density of this fluid is then purely governed by the free energy and not dependent on the transport coefficient, so that the equilibrium distribution for the two fields is just e to the minus free energy. Now, one of the ways in which you can think about that these so-called mode couplings, meaning these advection terms, arise is that you can think of them as being Poisson brackets. So again, you have these, in principle, four fields, except here we project on two of the components of the momentum density, and their classical evolution is just governed by kind of Hamiltonian equations of motion. And so that means they depend on the classical Poisson brackets of the fields with themselves. And these are by definition and some kind of antisymmetric. So you can work out what that antisymmetric matrix is, and it provides in particular these kind of mutual mode couplings between the phi and the pi field. And that's kind of important because we need both of these terms so that the fields can exchange energy. That, it's not one field pumping energy into the other, but you always need both of these terms. And it's this term in particular that's kind of beyond the accuracy of sort of ordinary Navier-Stokes theory, because the most relevant bit of this is, again, that now in the free energy, we have these kind of gradient terms. So there's an advection term in the momentum density that kind of contains third derivatives if you're near a critical point. But it's crucial that you keep this term, because if you don't, then the two fields cannot thermalize with one another. And then in addition to that, as I say, there's this kind of self-advection term, which is the ordinary unlinearity in the Euler equation. Okay. Just two brief comments. If you actually open Hohenberg and Halperin, he writes down a truncation of this theory where this self-coupling of the momentum density is actually dropped. And so I will call that model H naught. So that I made that name up. I don't know if that's a good name. So the self-coupling of the momentum density is dropped, and this model is claimed, again, according to Hohenberg and Halperin, to be in the same universality class. So they claim that even though generally speaking, this is obviously important, if all you care about is critical dynamics, you're allowed to drop it. And I will check that numerically eventually, whether that's actually true. And they have some kind of diagrammatic or some kind of power counting reason for saying that. There's also an obvious generalization where you actually keep all the components of the momentum density. So if you keep the longitudinal modes, then of course you're keeping sound, not just shear waves. And this theory is also claimed to be in the same universality class. And of course, it has a little more information. Like if you want to know what sound attenuation actually is, then you need to keep the longitudinal mode. So if you want to know what the critical behavior of the bulk viscosity actually is, then you need to keep these modes. And we actually looked at this at some point for the critical behavior of the bulk viscosity. Okay. So what is the issue with just somehow numerically realizing something like this? So in principle, I've actually tried this many times over the years because it seems super simple. If you just look at these equations, they're just the ordinary equations of fluid dynamics, potentially with the addition of a gradient term in the free energy density or the pressure. And so you would imagine that you can just take an existing dynamic code and literally just add one line, which is a call to a random number generator, that every time you compute the forces, you add that one line, you add a random number, and that's that, right? And then you just run the code. And I've tried this with a large variety of numerical codes that are out there in the cyberverse, and needless to say, it doesn't work, okay? And let me briefly explain what the difficulty is. And you can explain this by looking at the simplest of these theories, which is called Model A. It's called A because A is the simplest. So that's not even diffusion. There's a single order parameter field, and it just relaxes with some relaxation constant that's called big gamma. So that's model A, and then there's noise, and as usual, there's a fluctuation dissipation relation. So that's just some kind of stochastic PDE, and you can try to just discretize it. So you put it on a grid and you time step the fields. So the fields at some later time are the fields at the current time, and then there's some time step. And we somehow discretize, whatever derivatives are in there. So that's solving ordinary relaxation or fluid dynamic equations, but then we have to add the noise. And the noise will be some term of variance one, and then since this is, so gamma times t was the strength of it, but since it's a delta function, now that you have it on some grid, the strength of it is a sort of Kronecker delta, is the white noise, and the strength is 1 over the time step and 1 over the spatial step cubed. And then you sort of see what the issue is, right? So we now take the time step to 0 because we want to solve the equations accurately, and we take the spatial step to 0 because we want to have good resolution. And then this term becomes really, really big compared to this one. And that doesn't just happen in asymptotia, because in QCD, when people actually solve hydrodynamic equations because they want to do a good job, they take a fairly large, fairly small spatial step of a fraction of a Fermi. And if you just in your head do this little exercise of estimating that, if you think a quark-gluon plasma is actually made of particles, and you ask how many quarks and gluons are in one of your hydrodynamic cells, then the answer is, of course, less than 1, or even less than 1 in many cases, right? And that means, just from kinetic theory, you would expect the fluctuations to be 100% already in the place that you just completely non-critical fluid dynamics, the sort of code that you use to simulate it, has 100% fluctuations. And hydrodynamics is a very nonlinear theory. But then if you just run this with 100% fluctuation in every cell, it just blows up very quickly. Something bad starts to happen. And it's of course somehow inefficient, right? Because we know that in thermal equilibrium, these two terms actually kind of cancel, right? One of them is a diffusive step that takes energy out, and the other one is this noise step that puts energy in from some kind of heat path, and on average, they're just supposed to cancel, right? But one of them makes these enormous back and forth fluctuations, and the other one then has finite differencing in this on these enormous fluctuations. The one way to say this is that it's just very hard to numerically realize fluctuation dissipation relations, because everything you do about discretizing these derivatives and discretizing the noise tends to mess it up, okay? And that then also leads, there are these famous, everybody, when you start to read up on this stuff, you encounter this enormous literature on stochastic differential equations, and there's all this Ito and Strutanovich and so on. So these are all, if you wish, these are all ambiguities that have to do with exactly how you discretize it, because the noise is so big, everything matters, okay? So there's no what? Yeah, although frankly, I mean, they rarely really solve stochastic PDEs, right? There's an enormous literature on stochastic ODEs where they figured it out, but stochastic PDEs, they never do. And as a physicist, we actually kind of know the reason, because these are ultimately, by stochastic quantization, these are field theories. If you could actually prove that your scheme works, then you've successfully quantized QCD, right? And so in field theories, these things get significantly more severe. And I don't actually think that the math people know an answer, except in sort of very specialized theories. No, well, again, the only thing we actually know is that ultimately it should equilibrate into the free energy, right? Any scheme that will ensure, and that's of course what I'm about to do, right? Any scheme that ensures that this equilibrates to the correct distribution is a good scheme. And this whole Ito versus Strutanovich, I think from a physics perspective, is all some kind of nonsense, right? What it should really do is ensure that it equilibrates to the right distribution and it has diffusive behavior. Okay. And this, of course, what we're about to do, right? We should just ensure that A, we discretize these two things at the same time, so that fluctuation dissipation is automatically satisfied and that this thing equilibrates into the right distribution. And the nicest way to do this, at least I believe, is to use a metropolis update. So we make a metropolis update where the fields at the next step are the fields that, mhm, yeah, yeah. Well, I mean, again, that's the same statement, right? If you can actually carry out the stochastic quantization, then you can solve it, right? But in general, you don't know. And for most theories, it's not known, right? If you could actually solve it for interesting field theories, you could solve all sorts of problems, right? I mean, yeah, so this, all this is the stochastic quantization of various field theories, right? And if you could solve it in the general case, yes, but what I'm about to propose is much, much simpler than anybody ever does, right? And frankly, I don't understand why this is not done more often, because this is much simpler than what's in A, as far as I can tell, the cases that people can actually solve are very specialized. And B, what I'm about to propose is much simpler. And I don't understand why it's not done more frequently. Actually, I make occasional excursions to the stochastic PDE people in math departments and ask them why they're not doing this. And it's hard for me to get a decent answer out of these people. Now, okay, I think there is a sort of philosophical point, which is that indeed, as physicists, we understand that we ultimately don't really care about this process, right? All this math literature is about the question whether we can really make sense of this process, given that this is delta function noise. But as physicists, we understand that while it's all singular, it needs to be regularized. And the one thing we truly want is that it equilibrates into the right distribution, right? And that on long distances, it behaves diffusively. And that's not how they tend to think about this. They want to actually mathematically define what you mean by this equation, right? That's what they want. Right. And so that's, of course, I'll talk about this, of course, right? We're actually interested in this being real time, right? The sort of metropolis calculations that people actually run are, of course, designed to actually beat the critical slowing down, right? They hate that, but I want to measure critical slowing down, right? And so actual metropolis algorithms for scalar fields have all these cluster updates and so on, which are specifically designed so that they're not diffusive, but I want them to be diffuse. Right? I want this to be real time, not computer time. Okay, so I do the metropolis update, so I update by a random number, and then I reject accept by sampling against the free energy density. And the beauty of this is that this simultaneously realizes both the diffusive step and the random noise. Because if you ask yourself, what is the average update on the fields by this metropolis step? Well, it's kind of sort of equally likely to go up or down, but with a slight preference for lowering the free energy. So if you just average this equation of motion, it depends on the derivative of the free energy with respect to psi, and it wants to lower that. That's the diffusive step, right? If you naively discretize the diffusive step, that's what you intend to realize. And then, of course, there will be some noise around that, and the width of the noise is exactly what we want, right, from our differential equation. Mm-hmm. No, I mean, this, of course, is completely fixed, right? There's no freedom here because I want to realize the correct width of the distribution. Now, the one thing I can do is somehow change the time step, right? So I can make the time step smaller to get the acceptance rate up, or I can make the time step bigger. And in the metropolis, we actually will realize the correct equilibrium distribution no matter what we do about the time step. But this factor is not open, right? We need this to be this in order to get the correct width of the distribution. And the beauty of the metropolis is again, it will automatically, since we do an accept reject against the free energy distribution, it will automatically equilibrate into the correct distribution. Okay. Now the theory, again, it's still some kind of stochastic field theory, right? So it actually does have UV divergencies. So if we effectively regularize by putting it on a lattice of some sort, we still encounter these divergencies. So the parameters that appear in the theory, parameters like the relaxation rate or this mass parameter in the free energy functional, or eventually things like viscosity, they do get renormalized by short distance fluctuations, which means we somehow have to tune the bare parameters of the theory to realize whatever physical parameters we're actually interested in. So that part you cannot avoid. It's a physical effect, and we have to do it. Okay. So here's the simplest thing that you can do. Again, it's actually a terrible method to do the statics of a stochastic field theory because it has the critical slowing down in it, right? And so if you professionally want to measure a static critical exponent, you invent some algorithm that beats the critical slowing down, these famous cluster updates and so. So this is a terrible method for doing it. This is very, very expensive to measure static exponents because we actually have all the slowing down, but we should of course check. And indeed, we have to do one thing, which is we have to figure out where in this free energy functional the critical point actually is. So at mean field level, it's at m squared equal to 0, but this is a real, again, stochastic field theory gets renormalized, and we have to numerically find the critical point. And we actually, in practice, do this by looking at Binder cumulants in order to extrapolate quickly to the infinite volume limit. But the one thing you can then see is that if, for example, in one of my simulation volumes, I plot at the critical point the order parameter distribution, so this is here I called it magnetization, it's just a volume integral of the field, the order parameter field I plot this in some finite volume for different volumes, making it larger and larger than the distribution scale. But you open any textbook on kind of stochastic fields, and it tells you that this distribution at the critical point is supposed to collapse, provided you rescale by the volume and some critical exponents. Here, the ones that are relevant is the beta and the nu critical exponent. So I take the known critical exponents out of the literature, and lo and behold, it's not perfect collapse, but I get collapse. Okay? And again, the reason it's not perfect is because this is a terrible method for computing actual static critical exponents. What you also see, by the way, and which is kind of important in practice, so we looked at the same thing in something called Model B. Model B is the same as Model A, except the order now conserved. So that instead of a relaxation equation, this is a diffusion equation, right? That has two extra derivatives in it. But the statics is exactly the same, right? It runs off of the same free energy functional, so it has exactly the same static exponents, but the dynamic ones will be different. But it's also true that the actual order parameter distribution is different because now the order parameter is exactly conserved. So I have some big box, the total, the volume integral of the order parameter, I initialized it to be 0, it has to stay 0. Now it's conserving dynamics. So the only way I can make a histogram is I take a subvolume. So I take half the volume and show the magnetization in there, and I histogram that. And at the critical point, it looks totally different, right? It looks nothing like it. It doesn't have this bimodal anymore, but it collapses with the exact same static exponents, right? That's another example of that the actual universality is the same, but the order parameter distribution actually depends on what kind of dynamics you're doing. Because there's a conservation law now, right? So previously in this model A, the order parameter was allowed to fluctuate without any restrictions. But now it's a conserving dynamic, so meaning the total order parameter and the whole volume can never change. It's always exactly 0. Yes, so it has exactly the same critical point, right? But the actual order parameter distribution, if I histogram it in some kind of box, it actually looks different. And that's a well-known phenomenon. If you open kind of Binney's book, you can see the same plot. Okay, so now the thing that we can do that's actually new, so this was just finding the critical point and checking that everything is fine. So the thing we can do now that's new is measure the actual critical exponents. And it's believed in the literature that if you measure the dynamical exponents, meaning you measure the rate at which the system relaxes as you increase the volume of the system or as you increase the correlation length. So the way it was done in practice is that we always set exactly at the critical point, but of course we do it in a finite volume, meaning that the actual correlation length not be infinite, it just becomes some finite fraction of the volume of the system. And what we do is we increase the volume of the system and we ask how much longer does it take for the system to equilibrate. So we measure, say, the autocorrelation function of the order parameter. I'll write the formula down in just a second for model H. And then I ask how long, how much longer does it take to equilibrate or relax as the volume of the system gets larger. And for model A, again, at the mean field level, you would predict this to be exactly 2. For model B, that has 2 extra derivatives in it, so sort of anomalous diffusion at the critical point. So the mean field prediction would be 4. And the epsilon expansion says that it's actually very close to that model A just a little bit above 2, and model B is just a little bit below 4. And that's indeed what we see. So this is the logarithm of the system size on the x-axis, the logarithm of the relaxation time on the y-axis, and this looks like a pretty good straight line, which for model, again, same free energy, right? But model A dynamics, it's a little above 2, and model B dynamics, it's a little bit below 4. And again, what was actually done here is we measure the autocorrelation function of the order parameter field, and then I look for dynamic scaling. So I say if I did this in one volume, and now I do it in a bigger volume, so long as I scale such that the momentum leaves k times L the same, how much do I have to stretch the time axis? What is this dynamical exponent Z? And we just fit, right? Why is, I mean, you can do infinitely many things, right? Okay. Fourier transforming is pretty cheap. So here we look at modes of, I could do it in coordinate space. Here we do it for modes for some fixed frequency, right? So not really. I mean, but Fourier transforming is effectively free, right? Somebody invented FFT, so no big deal, right? And in the case of the actual model H, we use Fourier modes anyway in order to project on transverse components. So, okay, so now we do this for model H. Again, we need a conserving update on the fields. So the conserving update for the momentum density means we use metropolis on fluxes, not metropolis on momenta. So we have an accept reject step where I take 2 adjacent cells and my this momentum out once into the adjacent cell. I'm really doing metropolis on fluxes, and that will of course ensure that momentum is exactly conserved. And then I do exactly the same except reject with respect to the momentum density of the fluid. And now the one thing that turns out to be somewhat tricky is, so we have these advection or mode coupling terms now, which is sort of ordinary kind of Eulerian fluid dynamics, right? And of course we just ultimately will have to naively discretize these derivatives. But our field configurations are indeed now very rough, right? We have these fields that fluctuate by 100% from cell to cell. And that's not the sort of situation that's ordinarily imagined when somebody writes a kind of regular fluid dynamics code. Okay, they're somehow willing to entertain fields that have shocks in them. And of course, specialized literature on turbulence where you encounter similar issues, the sort of code that we typically use that was not written with this kind of thing. In fact, sort of codes that float around the heavy ion community, they have all these kind of flux limiters, steps, and actually have a fair amount of numerical viscosity if you have fields that are extremely rough. For ordinary field configurations, it's no big deal, but for this kind of thing, it's important. And so the particular thing that we ended up doing in order to ensure that again, these terms are supposed to conserve the hydrodynamic Hamiltonian, but if you just naively discretize, it's usually not that great. And so here we use a scheme that indeed was kind of invented by people who work on sort of turbulence and incompressible fluids, which is a fancy way of choosing derivatives so that various vector identities that in the continuum you would use in order to show that the equations of motion conserve the energy, that you preserve them on the lattice, right? They're not necessarily more accurate, but they actually exactly conserve the Hamiltonian. So there's some fancy way of using centered derivatives and sort of partial integrations to write these equations in a form. So the C means it's a centered discrete derivative, that the centered discrete derivatives actually conserve the hydrodynamic Hamiltonian. No, this just it's just the fact that we have some equations which in the continuum conserve energy, right? But if you discretize it, the proof that you use in the continuum no longer goes through because your discrete derivatives, it doesn't necessarily satisfy that the curl of a grad is zero and that, stuff like this, right? And so for fluid dynamics, there are, in ordinary kind of Hamiltonian dynamics, that's usually done using very symplectic schemes. And every so often we ponder whether something like this can be constructed for fluids. But at least the ones that are sort of out there are excessively hard to use. Okay, so this is what we came up with. Okay. Okay, and so here's just some kind of pretty pictures. So now we run the kind of full model H fluid dynamics. So this is just some three-dimensional simulation volume, and it's the order parameter where somehow green is in the ordered phase and blue is in the disordered phase. And here this is a two-dimensional fluid where I also then superimpose the local fluid velocity. So these arrows are the direction in which the fluid is flowing, and the green and the blue is the value of the order parameter. Okay? It's just some complicated system. It's near the critical point. Okay? So there's a variety of things that you can now look at, and the first thing we looked at is in these stochastic fluid theories, one of the first calculations was done is a really amusing calculation that demonstrates that indeed some kind of effective stochastic field theory, so everything gets renormalized. In particular, if you just compute a one-loop diagram like this, which is again the self-advection of the momentum density, it produces non-analyticities in the dispersion relation, but it also produces just a finite renormalization of the viscosity itself. And in typical calculations, we just cut this off by some kind of momentum cutoff that's called lambda. And the amusing thing that happens is the one loop graph gives a renormalization to the viscosity, which is inversely proportional to the bare one and linearly divergent in whatever cutoff you put onto the system. And so, again, historically, this was called the stickiness of sound. Here it's really just shear waves, right? So it's the stickiness of shear waves. And it means that, again, there's a sort of minimum viscosity in the system. As soon as you put a regulator on the system, the physical viscosity can no longer become arbitrarily small. Okay? And so this is very nicely seen in actual simulation. So this is actual model H and model H0 simulations, where as a function of the bare viscosity of the system, so the one that's actually in the code, I measure the physical viscosity in a variety of ways that beautifully agree. I can do it by actually putting in an initial shear wave and just let it evolve, do this a million times, average the profile, see the exponential decay, or I can look at the autocorrelation function of the some Fourier mode of the momentum density again that exponentially decays. I can read off the physical viscosity. And so here it's of course kind of one over the lattice spacing. Right? That's now the thing actually lives on lattice, so this lambda, I actually didn't repeat this calculation for kind of mode sum propagators, but if you did, you would see that it's some coefficient times 1 over a, okay? Which is so, and this is just a one loop calculation anyway, right? In a one loop calculation, when these two terms become comparable, then you didn't actually understand what you were doing. But qualitatively, this is in fact exactly what we see. So this is now this kind of physical viscosity as a function of the bare one, and regular model H is the top curve done in various ways. And so initially, if the viscosity is very big, then this 1 over eta doesn't do anything. So the physical viscosity is equal to the bare one, but if we start to drop it, then the physical one starts to no longer track the bare one and is significantly bigger, up to the point where you try to make the bare one 10 to the minus 3, the physical one never drops below 0.2. So this is in some dimensionless units, but the dimensionless units are actually effectively pretty close to eta over s. So loosely speaking, think of this as showing eta over s, right? And this particular effect really comes from this self-advection of the momentum density. If I discard that, I still see a renormalization. So this is this model H naught. I still see a renormalization, but it's much, much smaller. So the renormalization due to the coupling of the order parameter also renormalizes shear viscosity, but not by nearly as much. The dominant effect is indeed this graph. Well, there is a one loop, right? But it's just not the one loop with the momentum density, it's a one loop with the scalar field. But that has some more extra derivatives in it, so we would expect it to be suppressed, and indeed it is. No, No, it has no eta in it at all, right? It has scalar field propagated. And actually, I mean, nobody had previously computed this graph with the scalar field, and so I now did. And indeed, you can understand why that's smaller, and roughly speaking, that's because, again, the coupling is now has extra derivatives in it. This term is dropped, right? There's no self-advection of the pion field. It's only mutual advection of pi and phi. Okay. And so this diagram literally goes away. Okay. So I will show you that, right? I will have a beautiful graph that shows how this works. So you see here that the two, so again, Hohenberg says, oh, they're the same, right? But what he meant is they have the same critical dynamics, but this finite renormalization of the viscosity is much bigger in one than in the other. In that sense, they're actually very different. So now we can look at critical dynamics in this theory. There again, there is a sort of one loop diagram that people often compute in either the epsilon expansion or in what's called mode coupling theory. So there's a famous mode coupling theory for fluids, which is called the Kawasaki theory. And effectively what he does is, so this, in my notation, the solid line is the order parameter field. And the main process in the fluid is that it can couple, it can get dragged along by the fluid. So it couples to the momentum density of the fluid. And again, in my notation, these propagators with two lines as metric correlation functions. The propagators with sort of one arrow are retarded functions. So it's some fluctuation of the order parameter, and it gets dragged along by the momentum of the fluid. And if you compute this diagram and you try to do sort of self-consistently, meaning you put the full susceptibility, put the full static susceptibility in, but you do the dynamics kind of perturbatively, again, that's this funny mode coupling approximation. That's effectively what happens in the epsilon expansion. Here's what you get. You get some kind of relaxation rate that has two terms. One with critical slowing down that goes as correlation lengths to the fourth. That's effectively the model B piece, okay? That has a term that's ordinary diffusion, and then at the critical point, it's anomalous diffusion with the fourth power. And then it has a term that goes as 1 over xi cubed, and that again has a kind of 1 over eta in it. And so this 1 over xi cubed means that this theory predicts that the critical dynamics of model H has an exponent of 3, and then there's some complicated function that you can compute. Okay? So, but effectively what this theory predicts is that depending on what your viscosity is, if the viscosity is kind of large and the correlation length is finite, then you see model B-like behavior. As the correlation length becomes bigger or the viscosity becomes smaller, you see true model H behavior where the relaxation, the dynamical exponent is now 3. So it claims that there will be some kind of crossover from dynamical scaling with 4 to dynamical scaling with 3 in any fixed volume as a function of the physical viscosity of the system. So here I looked at a very, very small viscosity because that's where I'm supposed to see the best dynamical scaling. And I computed again this kind of correlation function of the order parameter as a function of time. I do it in different volumes, and I see if I can get dynamical scaling, meaning collapse if I scale the x-axis by some finite exponent. And what you see here is so two different volumes, it's 48 and 40, and so this gives different curves. But then I scale the curve in the smaller volume, the curve in the bigger volume by an exponent, which is close to 3, and then I get collapse. Right? And so my best attempt to quantify this give a dynamical scaling exponent of 307, which again, so Kawasaki predicts exactly 3, and epsilon expansion says probably slightly bigger than 3. We actually agree with that. But you also see this kind of crossover, right? It becomes 3 only at the largest correlation lengths or smallest viscosities. So this is as a function of the bare viscosity of the system, here purely in model H0. So in model H0, it's a little bit easier for us to get to small physical values of the viscosity because we can get it in a kind of a smaller volume. And so we see that there's this kind of crossover from exponents that are close to 4 to exponents that are close to 3. And it's actually, well, sort of qualitatively or semi-quantitatively described by this function that, again, you can see in the literature what it looks like. And now you can also see that indeed there is kind of universality, that I can do it in model H naught and drop the self-advection, or I can do it in model H and keep it. The physical viscosities will be different, but I can plot the same curve not as a function of the bare one, but as the function of the physical one, and I get data collapse, right? The two models ultimately give the same kind of scaling behavior. It's just that if you want to see the exact same exponent at a finite correlation length, you must plot them as a function of the physical viscosity, not as a function of the bare one. And you see that at very, very small viscosity, it's only model H naught points, because again, we have this finite renormalization actually prevents us from getting to really, really small viscosities. So the model H points somehow end somewhere. If I wanted to get them closer to 3, I would have to make the volume really big so I can get a really, really large correlation length. But that's actually the case, frankly. So the model H one is, of course, the more physical one, where the viscosity never goes on 1 over 4 pi, right? And these sort of volumes, okay, they're actually limited by what we could do on our computers. But again, they're actually sort of illustrative of what you could have in an actual heavy ion collision. So as usual, an actual heavy ion collision where your volume is finite anyway, and the correlation lengths cannot become infinite anyhow, you would never reach the 3. You would be somewhere at 3.5. So we can also look at the critical behavior of the transport coefficients themselves. So the easiest way to do that is to look at these Kubo formulas. So the Kubo formula for the thermal conductivity involves the correlation function of the current, and the Kubo formula for the viscosity involves the correlation function of the stress tensor. So we're still working on this. This is some preliminary stuff, and for simplicity, this was only 2 dimensions, but it just takes a little bit longer to run in 3 dimensions. It's true, by the way, that these calculations, you see that we don't do super large volumes, and the reason is that these dynamical exponents really are very large, right? So if I have a dynamical exponent of 4, what that means, it already costs me, I have the thing sitting on some lattice, the effort is already kind of L cubed just to visit every cell. But now there's also critical slowing down with an exponent of 4, meaning roughly speaking, the cost of these simulations is size of the system to the 7th power. Okay, it's physical effect, right? So you want to make it twice bigger, it's 1,000 times more effort. And so it actually, I started this thinking, oh, this is so brilliant, I just do it on my laptop. But okay, if you want to do a good job, it becomes kind of a high-end gaming PC, right? So okay, so here's an attempt to look at how these Kubo integrants scale. Again, we sit right at the critical point, so the correlation length is only limited by the volume of the system. And so I make the volume of the system bigger, and I see the scaling. So this is again log plot. See the scaling of the thermal conductivity and the viscosity with system size. And the exponent for the thermal conductivity, and again, that's known from the literature about fluids, it's much bigger. So in 2 dimensions, this one's close to a divergence with correlation lengths to the 1.6 power, whereas viscosity is pretty weak. So in 2 dimensions, it's an exponent of 0.3, and in 3 dimensions, it's expected, and our data seem to indicate it, even weaker, really, really weak divergence of the shear viscosity with a very small exponent. And what is really kind of nice, there are some hyperscaling relations that say that the critical dynamical exponent and this divergence of the thermal conductivity are not independent. They're related by static exponents. And our methods for measuring are really, they're not totally independent, but they're superficially independent. We measured this one from dynamical scaling of the autocorrelation function of the order parameter. We measured this one from the Kubo integrand for the current, and it's nicely consistent, right? It's another check that all of these symmetries are somehow actually respected in these calculations. What this shows is, again, just to show what is the real strength of this method. The real strength of this method is, number one, okay, it's currently running in a box, but okay, at least there's non-relativistic dynamics. We could just take the box off and do full fluid dynamics. For relativity, we have to think a little bit, but it allows you to do truly non-trivial backgrounds. Already with the code as it exists now, I could easily do a non-relativistic expanding system. And frankly, at the lowish energies, and you see that central rapidity, right? It's not that relativistic anyhow. I actually think it's credible to even just do a non-relativistic simulation if you're just doing it at a few GeV, but never mind. So that's of course one strength. This method can really handle some non-trivial background dynamics, right? Not just some kind of box. And the other one is that, if you do these sort of semi-analytic approaches like hydroplus or hydrokinetics or whatever people have done, it's very hard to go beyond two-point functions, right? It gets really, really messy. But here, you have an actual fluctuating fluid. There's nothing that prevents me except somehow statistics, but the same is true for the experiment to measure a 17-point function. So I can easily check, like, what is the decay of a 2-point function or a 3-point function or a 4-point function. So this is an example here. In some volume, I just measure the integrated magnetization, either the magnetization itself or the square or the cubed, and I just watch whether they relax at the same rate. And what is indeed very nice, they all relax with the same dynamical exponent, right? So if you measure the relaxation rate and I make it in a system twice bigger, I can read off the dynamical exponent from the decay of anything, right? I don't have to do the 1-point function. I can do the 15-point function, gives me the same scaling exponent. But the actual decay is, of course, not the same, right? And it's not even some kind of systematic thing. So the 1-point function decays the slowest, but the 2-point function decays the fastest, and the 3-point function is in between, right? So the actual exponents, there's not any kind of obvious system to them. It's just some numerical coefficient that you actually have to extract. And again, that's kind of relevant if the observables and actual heavy ions are somehow skew in kurtosis and stuff like this. This sort of scheme gives me very, direct access to actually measuring stuff like that. So, okay, so what we've done, I think we can simulate these, we can numerically simulate these stochastic fluid theories. We very nicely observe that indeed you renormalize the transport parameters when you do that. So you have to adjust the bare one to get the physical ones. For this model H, we obtain what is generally believed to be the correct dynamical exponent, which is this about a little bit bigger than 3. And of course, what we truly want to do is have some more non-trivial expanding systems coupled to a realistic background and embed this into relativity. And I think, again, for embedding it in relativity in the sort of most direct way while preserving most of the things we do, the obvious scheme, it seems to me, is this kind of density frame method. Okay, well, thank you so much. No, you still have field redefinitions, right? You still have field redefinitions, right? No, I mean, no, it's the same thing in a non-relativistic fluid, right? What you mean by fluid velocity is up to you. What you actually measure is the momentum density, right? That's the thing that's truly unobservable. So, I mean, we don't, or even also for the order parameter, right? Is it the entropy or the entropy per particle or the baryon density minus the critical one? Those are field redefinitions, right? The different choices for phi. No, well, okay, here it's not chiral dynamics, but even for the order parameter, right, you can do crazy stuff, right? You can do psi about times like weird or something, Now we haven't checked, right? But that's of course, if you actually did it, someone did field redefinitions that say involve higher derivative terms. Okay, you can also hit yourself over the head with a baseball bat, right? It's okay. In principle, it should all work, but okay, to actually see numerically that it all works could potentially be hard. Mm-hmm. Well, in principle, I mean, for these kind of near equilibrium situations, right, that was done. I mean, if you read in this kind of near equilibrium model ABCD, that was kind of done, right? There's some discussion, and again, if one just looks at Hornberg and Halperin of and again, this skew symmetric matrix that plays a role in this Fokker-Planck dynamics, right? So in principle, you can write this down, except I don't, it's somehow not a practical method, it seems to me, to actually compute anything. But just the mere fact, again, I mean, again, what does the Fokker-Planck do? It's somehow supposed to ensure that ultimately you just drift to this e to the minus f distribution. And in fact, that's the way, historically, I think people have thought about this, that the role of the Fokker-Planck is to convince yourself that this will do the right thing and ultimately relax to a Gibbs distribution. So in principle, one could, so again, the claim is that it's certainly at a critical point that it's all universal. Um, in principle, I haven't tried it, right? In principle, I think it's perfectly doable that we inject some noise that's not completely white. But yeah, I haven't tried it. And there again, I mean, I think the one thing one could potentially encounter, and I haven't thought about it at all, is again, for the purely white noise, again, we automatically respect everything in terms of fluctuation dissipation. For the non-Gaussian noise, there's no similar relations, right? There's additional transport coefficients, and there's non-Gaussian noise, and they're not totally independent. And again, the real question would be how to have a scheme that respects that. And I just haven't thought about it at all. Well, in principle, actually already somehow as usual, numerically not so easy. Again, we encountered this discussion last week, right? What is the ultimate behavior? Like is with cuts versus pole, right? We had this funny cuts versus poles discussion where somebody believed that ultimately it's all poles, right? Whereas the one loop calculations, it's all these cuts. And so in principle, I actually tried to see this, right? I can do non-critical simulations, even just with the leading order terms, I get these hydrodynamic cuts, meaning things don't decay as pure powers, they decay as fractional powers. But as you go to longer and longer times, it becomes sort of genuinely non-perturbative, and it's not obvious what all of these cuts eventually resum to. Okay. Now I can tell you that numerically, indeed, they resum to a diffusive pole. It's very hard to see this, but numerically, of course, it's also really hard to tell the difference because all we have is correlation functions with some finite accuracy. But yes, in principle, this is a tool to study some of these questions that we talked about last week. So that too, I mean, so ultimately that does indeed become relevant in an actual heavy ion collision, right? Here I treated eta as just a constant, ultimately it will become a function of the energy density, and I just haven't studied it. I mean, so diagrammatically, again, we know that everything's fine, right? We can do one loop calculations and everything is consistent. But yeah, I haven't thought about how this is, whether this is explicitly realized in the way we do it. Yeah, I mean, superficially, you would think so, right? I mean, yeah, I would think so. Hmm. No, but again, if you just, again, rerun my argument with gamma of psi, it seems to me that everything's fine, right? It will go through, and you're still doing metropolis against the correct distribution function, so everything should be fine. That too, again, in principle, we know, so I think numerically what may indeed be hard to demonstrate, in principle, we know that there are these extra like one loop corrections that in principle you should now be able to see. But okay, they're numerically actually not so easy. Some of them are not so easy to see. The dynamical scaling is really, I mean, what to me is actually frankly impressive. Again, So for model A and B, the exponents are very close to just mean field by 2 and 4. But model H is a pretty non-trivial theory because it's, you don't get cubic scaling out of anything that looks remotely mean field because everything is a function of k squared. It's hard to get k cubed, right? Again, the numerics, it all works. Hmm. Yeah. Well, you already get the non-analyticities without the multiplicative noise, right? No, that's not the multiplicative noise part. That's the part that you actually have in the free energy, higher than quadratic polynomials, right? They look at cubic, but okay, here it's actually quartic. So if you wish, they detuned it. But as soon as you have that, then indeed, you don't need multiplicative noise. You already get tails out of just non-polynomials with power higher than 2. Yeah, no, the multiplicative noise will change them, right? But it changes them in very subtle ways. So I don't, actually seeing that numerically might be kind of difficult. But yeah, in principle, I think this method could be used to study that. These are what? Yeah, yes. Yeah, so in principle, that's very, as I say, in some ways, we already did sort of similar studies where, you would measure a retarded function by just coupling the source, and then you turn it off and you watch it decay, right? And sometimes we already did sort of similar exercises of just initializing something and watch it decay. But yes, it's something one could do, explicitly measure a retarded function. Mm, mm. Well, the loops, of course, are important, right? In that they actually change the transport coefficients that appear to the physical ones, right? Mm, mm, mm. But as I say, I mean, I do checks that in some ways actually much more non-trivial checks already that this sort of stuff is satisfied. I mean, the sort of thing I showed you just a second ago, I cannot imagine that this would actually work if you messed up fluctuation dissipation because I measured one of them out of an order problem, the correlation function, and one of them out of a Kubo integrand, right? I don't think that can possibly work if you messed it up. At least diagrammatically, it wouldn't work, right? Hmm. But I mean, I take the point. I mean, right, I should actually start that function. No, I mean, we just haven't really done it, right? I can couple a source and, vary the source and measure the response. It's very physical, right? Mm-hmm. Mm-hmm. So, so in practice, the reason we did it is that so you get some violation of energy in the advection step. And you could say, oh, who cares, right? I mean, the sort of metropolis will eventually kind of repair it. It's already not the best because you actually see that in principle, again, the critical point of all of these models with different dynamics should actually be the same. The critical mass should be the same for model A dynamics, model B dynamics, and model H dynamics. If you mess up energy conservation in the advection step, you start to see that's not actually true, right? That's already unpleasant. And the real reason we did it is that the metropolis will tend to rethermalize the fields, but in if you simulate a very small viscosity, it does so inefficiently, right? And so if for whatever reason you made a really, you run a million steps, eventually you make a big mistake instead of a small one, right? And then if it's not absolutely unconditionally stable, then it can suddenly run away. And that would occasionally happen to us, right? The GPUs are churning away for hours, and eventually you encounter some rare fluctuation. You have no idea where it came from, right? And suddenly it runs away and crashes. And so this sort of thing ensures that that doesn't happen. That was the real reason we spent some time on it. Thank you.